on the morning of July 23rd, 2012, the sun opened up. Two clouds of magnetized plasma left the surface 15 minutes apart. They should have slowed down on the way out. They didn't. 4 days earlier, another eruption had already cleared a corridor through the solar wind, like a snowplow going ahead of them. So the two clouds merged and ran that empty corridor at more than 2,000 kilometers per second, roughly 4 times the speed of an ordinary storm. They crossed the orbit of Earth in about 18 hours, not near Earth, through the exact ring of space our planet moves along. Nobody panicked, nobody wrote about it. There was no warning issued because there was nothing to warn anyone about. Earth had already gone past that point a little over a week earlier, and it would take 2 more years and one spacecraft standing in exactly the wrong place before anyone understood what had just gone by. The spacecraft was called Stereo A. It wasn't built to survive that. It was built to watch the sun from a different angle than we do, and it happened to be parked directly in the path. So it measured the whole thing: speed, density, magnetic field strength, every number from inside the cloud. That is what makes July 2012 different from every other conversation about extreme space weather. Every other one is a model, an estimate, a worst case assembled out of assumptions. This one is a measurement, and the measurement puts that storm in the same class as the largest space weather event in recorded history. So there are 3 questions worth the next 20 minutes. What exactly went past us? Why nobody noticed for 2 years? And why the honest answer to how bad would it have been has very little to do with the sun, and almost everything to do with a supply problem nobody talks about. Start in 1859, September the 1st, 1859. Richard Carrington is 33 years old, and he is doing what he does every clear morning. He isn't a professional astronomer. He runs a brewery he inherited, and he built himself an observatory in Surrey, south of London, so he could work on the sun before the working day started. His method is simple, and it hasn't changed in years. He projects the sun's image onto a screen about 11 inches across and traces the sunspots by hand, one by one, on paper. That morning, there is an enormous group of spots. He has been tracking it for days as it rotates across the face of the sun. At 18 minutes past 11, 2 points of white light appear inside the spot group. Not bright, blinding, brighter than the surface of the sun behind them. Carrington's first thought is that something has broken, that a cloud has moved, or the screen has slipped, or a lens has cracked. He runs out of the room to find another witness. He is gone under a minute. When he gets back, the 2 points have moved and shrunk. 5 minutes after they appeared, they were gone. 17 kilometers away, another English astronomer, Richard Hodgson, saw exactly the same thing at the same moment and had no idea Carrington existed. 2 men, 2 instruments, 5 minutes. What they watched has a name now: a white light solar flare. In more than a century and a half of continuous observations since, only a handful have ever been recorded. Carrington was a careful man. In the paper he published, he refused to claim that what he saw and what happened next were connected. One swallow, he wrote, does not make a summer. He was being modest. 17 hours and 40 minutes later, the sky went wrong. Auroras, not at the poles, over Cuba, over Hawaii, over Panama, 8 degrees off the equator. In the Rocky Mountains, gold miners got up in the middle of the night and started cooking breakfast because the sky was bright enough that they assumed it was dawn. In Boston, people read newspapers by it, outdoors, at 1 in the morning. And underneath all of that, the telegraph network, the first electrical nervous system human beings ever built, started behaving as if something else was operating it. Operators in Boston and Portland found they could disconnect their batteries completely and keep sending messages down the line. The Aurora was powering the wire. They kept working that way for about 2 hours. In other places, it went the other direction. Sparks jumped from the equipment onto operators' hands. Paper caught fire inside telegraph offices. Lines shorted out. Men were thrown back by shocks they still talked about decades later. Here is the part that actually matters. In 1859, the entire electrical infrastructure of the human species was copper wire on wooden poles, carrying dots and dashes. There was no power grid, no transformers, no satellites, no GPS, no data centers, no refrigeration, no pumps moving water into cities, or fuel out of the ground. The storm hit the only electrical thing we owned and set it on fire. We rebuilt in days because there was almost nothing to rebuild. That is the whole reason the Carrington event is remembered as a curiosity instead of a catastrophe. Not because it was small, because we were. So for 150 years, 1859 sat at the top of the list, the benchmark, the worst thing the sun had ever been observed doing. Then Stereo A handed over the numbers from July 2012. There's a measurement called DST. It tracks how far Earth's magnetic field gets pushed out of shape during a storm. The deeper the negative number, the worse the event. The storm that took down Quebec in 1989, the worst of the entire space age, came in around -600. Estimates for the Carrington event run from -800 to -1750. It's a range that wide because nobody in 1859 had instruments. The July 2012 event reconstructed from direct measurement inside the cloud, comparable to Carrington, possibly past it, which means 1859 was never the ceiling. It was just the last one we happened to be standing in front of. You don't need a simulation to know what that would do. There's a real test. It's short. It's documented minute by minute. And it happened at 2:45 in the morning, March 9th, 1989. A large active region on the sun produces an X-class flare and throws a cloud of magnetized plasma straight at Earth. It covers the 150 million kilometers in about 55 hours. Fast, but not extraordinary. What is extraordinary is its orientation. The magnetic field inside the cloud is pointing sharply south, the exact opposite of Earth's own field where they meet. That is the worst possible configuration. It lets the two fields connect, and it lets solar energy pour into the upper atmosphere instead of sliding around it. The cloud arrives late on March 12th. Now, geography. Quebec is unusually exposed for reasons that have nothing to do with Quebec. Hydro-Quebec runs 735 kilovolt transmission lines over the Canadian Shield. Some of the oldest, hardest, most electrically resistant rock on the planet. When a geomagnetic storm drives current into the ground, that current looks for the easiest path. Over the Canadian Shield, the ground is not the easy path. The power lines are. At 2:44 in the morning, Current starts flowing into transformer windings that were never designed to carry it. The magnetic cores push towards saturation. Reactive power demand jumps. Distorted frequencies, harmonics, start moving through the network. Protective equipment reads that as a fault and begins disconnecting sections to save them. Each disconnection loads the sections still standing. The whole thing takes 90 seconds. 21 gigawatts of supply gone. 6 million people without power and without heat. In Quebec, in March, at 3 in the morning. Most of them were still asleep when it happened and only found out when they woke up. Montreal's underground network went dark. Traffic signals stopped. People got stuck in office towers and in lifts. Most customers had power again within about 9 hours. Some industrial sites, smelters, pulp mills, waited considerably longer because their loads were too heavy to reconnect to a grid that was still finding its balance. And while that was happening, auroras were visible from Florida, from Texas, from Cuba. Some people who saw them assumed they were watching a nuclear exchange. 9 hours, one province. That's the story everyone tells. It's the wrong story. 1,500 kilometers south of Quebec, the same night, the same storm did something else. At the Salem nuclear plant in New Jersey, a generator step-up transformer, the machine that takes the plant's output and pushes it up to transmission voltage, took induced current through its windings. The windings overheated. The insulation was permanently damaged. No blackout, no headline, no province in the dark. One machine quietly destroyed in a building nobody was watching. Quebec had its power back in 9 hours. The transformer never came back at all. It had to be replaced. And that is the real shape of this threat. Not the lights going off. Lights come back on. The question is, what got cooked while they were off? And how long it takes to replace it. Extra high voltage transformers are not products. You cannot buy one. Each is designed for one position in one network. Voltage ratio, impedance, cooling, the physical footprint of the pad it sits on. All specified for that site. They weigh in the hundreds of tons. A large one is heavier than a fully loaded airliner, and it does not come apart into convenient pieces, which creates a second problem that has nothing to do with electricity. Moving one requires specialized, heavy rail cars, and there are not many of those in existence. Bridges have to be surveyed. Routes have to be approved. Roads sometimes have to be reinforced first, and they are built to order by a small number of factories worldwide. Historically, the wait has been measured in months at best, and closer to a year as a normal case. Salem got lucky, and the luck is the interesting part. A spare unit happened to exist. Accounts differ on how quickly it actually went into service. Some say weeks, some say months. But every version agrees on the thing that matters. There was a spare. Without one, the estimate was about a year. One transformer, one plant, on a night when the storm was roughly a third as strong as what missed us in 2012. Now change one variable. Utilities keep spares the way you keep a spare tire. One, maybe two, because transformers fail one at a time from age or a fault or a lightning strike. A severe geomagnetic storm does not fail them one at a time. It drives current into every long conductor across an entire continent in the same hour. The spares are singular. The failure is plural. That is the gap, not the storm. The gap between how we hold inventory and how this particular thing breaks. If you're still here 14 minutes in, this is what this channel does. One subject taken all the way to the bottom. Subscribing costs you nothing, and it's the only signal that tells me to keep making them. So, how much warning would we get? That question has 3 answers, and only one of them is useful. The flare itself arrives at the speed of light, 8 minutes. By the time you can see it, it has already done what it's going to do to radio and to the upper atmosphere. Energetic particles come next, under an hour. Those are what damage satellites and put astronauts at risk. The cloud itself is slower, 17 hours and 40 minutes in 1859, about 55 hours in 1989, around 18 hours in 2012. So on paper we get most of a day. That sounds workable. It isn't, and here's why. The single parameter that decides whether an arriving cloud is a light show or a grid emergency is the direction of the magnetic field inside it. Pointing north, it mostly slides past us. Pointing south, it couples, and the energy goes in. We cannot measure that from here. We measure it when the cloud reaches the spacecraft parked upstream of us, about 1.5 million kilometers out. At the speed these things travel, that gives operators somewhere between 15 and 60 minutes. A day to see it coming. Under an hour to know whether it matters. The obvious question is how often this happens. In 2012, a physicist named Pete Riley worked through the historical record of geomagnetic disturbance and put a number on it. Roughly a 12% chance of a Carrington-class event in any given decade. He said himself he was surprised the figure came out that high. It's an estimate built on a thin record, a century and a half of data for an event we have seen once, treated as an order of magnitude, not a forecast. But here's what has changed since 1989, and it isn't the sun. February 2022. SpaceX launches a batch of Starlink satellites into a geomagnetic storm that was, by any historical standard, minor. The storm warmed and expanded the upper atmosphere. Drag increased. Most of that batch, around 40 satellites, never made it to operational orbit. A minor storm. 40 spacecraft, May 2024. The strongest storm in about 20 years. Auroras over places that had never seen them. The grids held, which is genuinely good news, and worth saying, because operators have spent 35 years since Quebec building procedures for exactly this. But across the American Midwest, GPS-guided tractors stopped working accurately in the middle of the planting window. Not a catastrophe, a signal, a demonstration that the number of things quietly depending on space is now much larger than the number of things anyone is tracking. And that storm was still far below Carrington class. Which brings back the second question from the beginning. Why did nobody notice July 2012 for 2 years? Because we never saw it from the front. We saw it from the side, through an instrument that was there for another reason entirely. The analysis took until late 2013 to publish, and until 2014 for anyone outside a narrow specialty to hear about it. There was no siren. There was no emergency. There was a paper. The most powerful space weather event in 150 years passed through the road we drive on, and it entered public awareness as a footnote 2 years late. Go back to July 23rd, 2012. 2 clouds leave the sun 15 minutes apart. They run a corridor that another eruption cleared 4 days earlier. They cross Earth's orbit at over 2,000 kilometers per second. And Earth is not there. Not because of any defense, or forecast, or decision. Because of where we happen to be on a circle we complete once a year. The region of the sun that produced it wasn't pointing at us that week. the Sun rotates roughly once every 25 days at the equator. Move that event a few days either way in the rotation, and the geometry changes completely. Daniel Baker, the physicist who led the analysis, put it in one sentence when the study came out. If it had hit, we would still be picking up the pieces. That was said in 2014, 12 years ago now. What I keep coming back to isn't the storm. It's that our safety on that particular week was a matter of timing, of orbital position, of where a rock happened to be along its track. We tend to think of the solar system as scenery, something stable that we live inside of and that stays where we left it. It isn't scenery, it's machinery. It has moving parts, and the parts have positions, and the positions decide things. And one of those parts is leaving. The moon is moving away from Earth, not metaphorically, measurably, by about 3.8 centimeters a year. And we know because we bounce lasers off mirrors left there in the 1970s. It is slowing Earth's rotation as it goes. It is lengthening our days. And it has already set an expiry date on the total solar eclipse, a date after which no one standing on this planet will ever see one again. That's the next one.